Principle of superposition. So here is our learning outcome. Understand and apply the principle of superposition. Principle of superposition. The resultant stress or displacement at a point can be determined by finding the stress or displacement due to each component load acting separately and then adding the stresses or displacement due to each component load. So in the diagram, we can see that the total deformation is equal to the deformation of 1 plus the deformation of 2. So if our axial force is equal to P1 plus P2, for deformation to equal deformation of 1 plus deformation of 2 to be true, we need our elasticity of 1 to equal the elasticity of 2, which equals our total elasticity. And our area 1 plus area 2 has to equal our total cross-sectional area. And our length 1 plus length 2 has to equal our total length. Then our deformation is equal to our deformation of 1 plus deformation of 2, which is equal to P1 times L divided by AE plus P2 times L divided by AE. This simplifies to our equation of P times L divided by A times E. The same thing applies for sigma. If stress is equal to stress at 1 plus the stress at 2, which is equal to P1 divided by A plus P2 divided by A, which simplifies to our force divided by A. So now let's look at a visual example of a beam supported by a pin support and a roller support, creating reaction forces of AX and AY and BY. So to solve for BY, we can break down the forces into P1 plus P2. So by taking the moments about point A, we can solve for the force in the y direction at B, which is equal to P1 divided by 3 plus 2 times P2 divided by 3. So by breaking down the beam into its sections of P1 and then looking at the force that's acting at P2 alone, we can find the total force in the y direction at B by summing up By1 plus By2. So here are some key points to know if the principle of superposition is valid. So it's only valid if the load is linearly related to stress and displacement. So you have to make sure that it's linear elastic behavior and Hooke's law is applicable. If so, you can subdivide the loadings into components and then add its results. Next, the loading must not significantly change the original geometry of the added results. The deformation under the loads are small in comparison to the geometry of the structure. So here's your example. The steel pipe has an outer radius of 20 millimeters and an inner radius of 15 millimeters. If it fits snugly between the fixed wall before it is loaded, determine the reaction at the wall when it's subjected to the load shown. So first we start out by drawing a free body diagram. The diagram shows the steel pipe with two reaction forces at the fixed walls, Fa at point A and Fc at point C. The 16 kilonewton load is applied 300 millimeters from the left end. So the purpose of this is to establish the forces acting on the pipe to apply equilibrium conditions. Step 2 is the static equation, so summing the forces in the horizontal direction. We have Fa minus 16 kilonewtons plus Fc. This equation represents static equilibrium, ensuring the system is in balance. Step 3 is the compatibility condition. Since the pipe fits snugly between the walls, the total deformation of the pipe must be 0. So this condition ensures no net movement occurs, so any compression in one section is offset by an extension in another. Step 4 is the internal force calculation. So when looking at each segment, AB, we have PAB is equal to the force at A. And for BC, PBC is equal to the force at C. These internal forces are crucial because they contribute to the deformation calculations. So next, to take a look at the deformation analysis. By using the deformation formula for each segment, we have the deformation at AB is negative PA times 300 divided by AE plus PC times 700 divided by AE. Note that the negative sign for the deformation of AB represents compression, while the deformation for BC is positive, so it's in tension. So since the deformation of AB plus the deformation of BC is equal to 0, we can combine the two equations. And since A and E is constant, we can simplify this now to solve for the force at A and the force at C. So substitute FA is equal to 2.33 FC into the earlier statics equation. This gives us a result of 4.8 kilonewtons for the force at C. Then we can solve for the force at A, which is 11.2 kilonewtons. In the summary, we looked at how the principle of superposition is applicable only for linear elastic materials, where stress is proportional to strain. Next, the superposition simplifies complex loads cases by breaking them into smaller, manageable components, and their combined effect assumes that individual effects do not interfere with each other. So, if a bar is subjected to two forces, P1 and P2, the total deformation is given as the total deformation is equal to the deformation of 1, which is caused by P1 acting alone, plus the deformation caused by P2, which is acting alone.